My favorite chapter. I look forward all year to be able to teach this chapter. My favoriteest. Redox and electrochemistry. Just the best. Really, electrons traveling, balancing. It combines everything we love. G's and K's and Q's and H's and S's. It's like all at once. It's amazing. Okay, maybe it's just me. That's fine. Alright, reminders, you have a mastering due Friday night. By the end of today, you can do all the stuff that's on the mastering for Friday. But I wanted to give you an extra day, right? So the mastering's due Friday night. You can certainly do it today. You have an exam coming up. You have a group quiz on Friday. And I wanted to remind, in case you hadn't heard about it, there is a geology climatology talk tomorrow night in here, 7 p.m. Counts for CE credit, but you could also use it instead of a TED talk. If you're going to come anyway, you could listen to it, summarize it, and it'll count for a drops quiz, depending on how many TED talks you've done. So, that is an option. You get to double dip, right, because it's CE credit. So, done my public duty. Excellent. Alright, so let's talk about redox chemistry and electrochemistry. Alright, so this area of electrochemistry is the study of the interconversion of electrical and chemical energy. It's how we convert electrons moving into energy, right? It's how your car works and how everything in general works. You're converting a chemical reaction into some sort of useful physical energy. So, right, electrical reactions are going to be able to do work, right? You could move something. You could use it to complete a reaction, encourage it to go to completion. You could use it if you need it to produce heat. That's a possibility too. If you've used your cell phone too long, right? The battery on the back is hot. Electrochemistry at work. Or we could use it just to produce electricity, right? So electrical energy is not necessarily electricity, but you could use it to produce electricity. Alright, there's two different ways that we can do these reactions, and we call them cells, and you'll see here why in a minute, why we call them cells. One way we can do it is using what's called a voltaic cell. Alright, if it's a voltaic cell, it's spontaneous reaction. And its main function is to be able to generate electricity. Alright, so when you think about battery, right, its job is to produce electricity so you can use it for something. Those are voltaic cells. If it's spontaneous, what should the sign of delta G be? Negative. So obviously these are going to be very related. Everything in this chapter is going to deal with G's and H's and K's and Q's and S's and things. Alright. The other option is something called an electrolytic cell. Guesses on if this should be spontaneous or not. This one should be non-spontaneous, right? So these reactions are non-spontaneous. They use electrical energy. So it's going to use electrical energy to complete the reaction. These are typically things like electroplating, right? So if you have a gold-plated ring or earrings or whatever, how they get the gold on there is they put the thing into a bath of gold metal and force electricity through it and it gets stuck to the ring. So, or titanium plated. Anything that has the word plated afterwards has been stuck in a bath of the metal, and by forcing electricity through the bath, it gets stuck to the object that you want. So, we're going to look at voltaic cells the majority of the chapter, and at the end of this chapter we'll look at electrolytic reactions and what they're good for. Alright, so let's take a look at what is a voltaic cell. Alright. Oh, am I out of order? Hold on. Alright, we can do this. Okay, yeah. Alright. Let's take a look at, well, this is going to be a voltaic cell anyway. Let's look at an electron transfer reaction in a voltaic cell and look at how the electrons are being moved from one side of the arrow to the other. Alright, so given this reaction, I have copper solid and silver ions going to make copper ions and silver solid. So far, so good? Alright, we know that this is an electrochemical reaction because the oxidation states have changed. Alright, so if I look at the silver, its oxidation state is +1 and it's going to 0. Alright, so that's a dead giveaway. That only happens if it's a redox reaction. So, let's talk about some of this lingo. Alright, so first part of the chapter is going to be a bunch of like just new words. Alright, so reduction is a reaction where electrons are consumed. Right, they are going to be used to do something else. So if they're going to be consumed, should they be a reactant or a product? They need to be on the reactant side. Alright, if I have an oxidation, this is a reaction where electrons are produced. So where should I look for electrons if I know it's an oxidation reaction? Product side, right? Alright, so you can have a reduction reaction, you can have an oxidation reaction. What should be a redox reaction then? Both are happening simultaneously. Alright, so the majority of the time we're going to be looking at redox reactions where both of those things are happening. Something's being reduced and something's being oxidized. Alright, Alright, so determine what is being reduced and or oxidized. I guess it can't be and. We're going to split a whole reaction into two half reactions. Alright, so what I have up here is a whole reaction, right? It's all kinds of balance. Mass balance, charge balance. But it's hard to see who's being oxidized and reduced, so what we're going to do is we're going to split these into two half reactions and better label them. Where do I have that? Hold on a second. Okay. Alright, so let's look at this reaction again. Looking at copper, silver, making copper, silver. Alright, if I want to split into two half reactions and I want to start with copper solid as a reactant, what should be the only product it makes? Right, okay, copper ion, good. Okay, so that would be a good half reaction. That's all the things that are copper, but it's only half of the stuff. Right, so that would be a half reaction. So then what should the other half reaction be? Right, the silvers. Alright, so these are both half reactions. Right, neither one of them by themselves is the whole story. Each of them are half. Alright, let's take a look at the copper. What is the oxidation state of the copper solid? 0, right? It's given to you. 0. What if it wasn't given to you? How would you know it's 0? It's in its normal natural elemental state. So copper is normally found at room temperature as a metal, so its oxidation state should be 0. Alright, what's the oxidation state of this copper ion? 2+, right? So, if I need to add electrons to make both sides equal in charge, where should I put the electrons? And then how many? 2. Right? So now I have an oxidation state of 0 over here. And over here I have 2 pluses, but now I have 2 minuses. So now everybody's equal to 0 on both sides of the arrow. Alright? So if I put the electrons as a product, what reaction is this? The oxidation or the reduction? Reduction. Okay. Electrons as a product means this is the reduction. Oh, well, hold on. No, sorry, oxidation. Sorry, I was looking ahead at my notes. Oxidation. Just kidding, just kidding. Good listening. Good listening skills. Alright, what is the other thing that is happening to the copper? If I was looking at 0 to +2, has the oxidation state increased, decreased, or remained the same? 0 to +2 is an increase, right? We would consider that, looking at your number line in your head, 0 to +2 is considered an increase. The other way you know it's an oxidation state is that the oxidation state has increased. So oxidation have increasing oxidation states. Always true. Question. No, going from 0 to +2. Yeah. Yeah, the number has increased. Alright, so let's look at the silver. What's the oxidation state of the silver as a reactant? Each plus 1, altogether plus 2. What is the oxidation state of my solid? 0. Has my oxidation number increased, decreased, or remained the same? It is decreased. Where do I need to put electrons to get this to balance out? Yep, I need 2 over here. So electrons have gone in. So reductions have a decreasing oxidation state. So the electrons go in as a product, and overall my silver went from plus 1 down to 0. So far so good? If I were to add these two reactions together to get my original reaction back, what happens to those electrons? They cancel out. So when you do these, right, if you looked at this original equation up here and you're like, I don't understand why you need 2 silvers on either side. Looking at the charge, it'd be, well, that's why, right? 1, you have to have the charge all balanced out, right? On this side, you have 2 plus. Now on this side, you have a 2 plus. So you have to have 2 silvers, and the 2 silvers have to have 2 electrons. So all the electrons, there should never, ever, 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 never, ever be an electron left over in an equation. There are no free electrons in what we do. They're always all used up. Alright, so, okay. No, I'll save that. Yep, I'll save all that. Let's just balance. Alright. Let's take a look then at how to balance things. And we'll just do tons and tons of balancing problems, and I'll talk a little bit about how we figure this out. Alright, so now I have aluminum solid reacting with copper plus 2 to make aluminum plus 3 and copper solid. It is currently not balanced. Right, in terms of charge, how much charge is that product? 2, right? I got, oh, sorry, it's a product. 3, 2, so we're obviously not balanced. I have to figure out how to balance it. So in order to do that, I have to break it into 2 half reactions. Let's do, I guess, the aluminum side. Alright, the aluminum oxidation state was not given, so what do we know it has to be? It has to be 0, right? Because aluminum at room temperature should be a solid. So, it's assumed to be a 0. Where do I need to put some electrons to get this all balanced out? As a product, how many electrons? 3. Right, so now I have 0 on this side, and these two will add together to make 0. I have electrons appearing as a product, and what has happened to my oxidation state? Right, it's increased. So is this the oxidation or reduction half reaction? That's the oxidation. Alright, so let's take a look at the copper half. Alright, what's my oxidation state of the copper ion? 2 plus. What about this guy? 0, right? Because copper should be a solid at room temperature. Where do I need to put some electrons to get this all balanced out? Yep, and I need 2 of them. So, is this a reduction reaction? Okay. what would happen if I added these two halves together right now? It wouldn't work, right? I have leftover electrons. How do I solve that problem? So I need to multiply this whole thing by 2. And I multiply this whole thing by 3. And by doing that, now I'll have 2 of these and 3 of those. And 6 electrons, making which you could have kind of seen, right, based on the fact that you had 2 and 3 charged at the top. I mean, you kind of could have worked through it like that. Questions on this one? Feel like we're ready for a trickier one? Question first. Well, then it'd have to tell you the oxidation state. Yeah, if they don't, it's typically 0. Alright, let's try. Are we ready for this one yet? No, we're not ready for that one yet. So the next one's in your PowerPoints we're not ready for yet. We're going to work up to that. Let's look at that'll be a good one. Alright. I thought I'd just go to 0 to 100, because I think you guys got it. Alright, so here we have chromate and iodide making a chromium and an iodine in solution. What are several of the things that look wrong about this currently? In fact, they are. Everybody's switching states. Excellent question. That is one of the issues. One of the issues is no oxygen. What's another issue? Charges. Charges are all messed up, right? This is the chromate. This is chromium. Yeah. The same guys. Alright, because it's an ion. Has to be aqueous. All kinds of conundrums, right? Is it easily balanced by eyeball? No. So we're going to have to go through a longer process to be able to solve this. I love these things. Alright, we can do it. We can do it. Okay, here we go. Alright. What half would you like to tackle first? Okay, right's not an option. Well, we can do the chromium. Alright, so let's look at these guys, the chromate, the chromium ion. First question we have to figure out is what is the original oxidation state of the CR? CR. For sure it's over here is +3, right? That seems pretty straightforward. Question first. Nope. Let's work through it. Okay. Remembering back to 108, whenever you last took it, if oxygen was an ion, what should its charge be? 2 minus, right? Oxygen always 2 minus. I have 7 of them. How many charges should 7 oxygens have if they're each 2 minus? 14. Alright, so this is going to be minus 14. If you know the whole thing is minus 2, what does this have to be so that it ends up being minus 2? 12. So this side is plus 12. If I have 2 chromiums, what do they each need to be? Plus 6. So this got to start off is plus 6. An individual CR is a plus 6. It's going plus 6 to plus 3. That increase, decrease remains the same. Decrease, right? It's a decrease in electrons. Each chromium needs how many electrons to go from 6 to 3? Okay, 6 to 3 is how big of a jump on your number line? 3, and I have 2 of them, so altogether I need 6. I need 6 electrons. Oh, that's right. No, that's right. Because I have plus 12. We haven't balanced it yet. Right. Right, because I also need this. Right, that's the other thing that's missing. I have 2 chromiums on this side and only 1 on that side. I only had 2, and I know for sure I have 2. I have to have 2 in there. Alright, so let's think through that again, right? Altogether, these 2 chromiums are plus 12. They each have to be plus 6. Plus 6 to plus 3 is 3, and I know I need 2 of them. So I need 6 electrons. So that takes care of the CR. Right, the CR is looking good. Now let's talk about these pesky oxygens. Except that'd be catastrophe because now you're not balanced. Let's see, 63. Yeah, 3 dots. We'll get there. Let's talk about oxygen. We'll do all the oxygens, then we'll talk about which one it is. Should start with the iodine, so it's easier. Alright, so the key to this part of the question is balance in acid. If you are in an acid, what sort of things should be floating around near you? Right? Some of these, and what is the only other thing that should be in there, theoretically? Water. So we're going to assume that the only things in there besides this reaction are H pluses and waters. Is that a good assumption? Not really. That's a terrible assumption. Should be hydronium in water. There should be hydroxide. But we're not ready for that. That's going to be later. Probably tomorrow. Probably Friday. We're not even close. We'll work on our number line first, and then we'll work up to everything else. Alright, so how many oxygens do I have going into my reaction? 7, right? I can only use H pluses and waters to balance it out. Which of those 2 contains oxygen? Water. Good. Trying to throw like little tiny softballs at you guys. Water. Water has oxygen in it. If I have 7 oxygens over here, what should I maybe have as a product? How many waters? 7 waters. Look, now my oxygens are taken care of. How do I fix the hydrogen? Yes, how many? Oh, 14. Done. I have 7 H2s. We're going to do a bunch of these. A bunch of these. Oh, because we assume it's only H pluses and waters. Just makes it easier. Alright, so now the question is, have we fixed the mass balance issue? We haven't done iodine yet. So for this half, have I fixed it for this half? Good. Okay, let's do the other half. You can see why I love it. It's like little puzzles. Like you're trying to figure out how to balance it, get all the charge right. Alright, what is the easy issue that is wrong with this current half reaction? How many iodines do I have here? And then how many iod? 2. So if I do this, that's a good start. What's the oxidation state of these I's? -2 altogether. What's the oxidation state of this I? 0. Where do I need to put electrons to balance it out? How many? Have I successfully balanced its charge and its mass of that half? Right, that's the easier half. We should have probably done that first. Alright. Right this second, can I add these two half reactions back together? No, I need to fix it, otherwise I have leftover electrons. Do I need to do anything to this first half? No, what do I need to do to the second half? Multiply by 3. So now, I should have to get the electrons to cancel out. Space. Oh yeah, sorry, that should be a 6. Yep. I just was thinking I wrote way too big. Question. Oh, no, we took care of that by saying that that half only had 12. Right, so the original -2 comes from the fact that oxygen, 7 of them is -14, and if the end result is -2, this can only be 12. You could do it the other way, but I think you end up with errors later. I think it's easier to say, this is 14, that's 12, so altogether it's -2, and then those 12 are each 6. You just leave them alone. Yep, they're just hanging out in there to keep everybody balanced. That would be the end. Ready to do another one? I think we got it. We got it. We'll do another. What is that? Do a simple one? Yeah, it's going to be the exact same thing, just different compounds. Okay. And then we'll see what time it is when I finish that. Alright. Let's do I'll do this. Alright, so let's balance the outset again. Alright. Which half would you like to look at first? The half with bromines or the half with tin? Tin's the easier half. Let's do that one first. Alright, so I have SN2+. Alright, I've gone from tin plus 2 to tin plus 4. Have I increased or decreased my oxidation state? Increase, so is this an oxidation or reduction half? Oxidation. What's the other thing I have to do to tell you it's an oxidation? Where do I need to put the electrons? As a product, how many? Done. Looking good there. Feel confident about that. Okay. Let's look at the other half. What is the first thing we have to figure out before I can start adding electrons anywhere? Right, I have to figure out what the charge in the bromine is in the compound. Alright, again, I have oxygen. Oxygen normally comes with what charge? -2. I have 3 of them. So that, all those oxygens together should be -6. If the overall molecule is -1, what is the bromine half? +5. Pretty much you always start with the oxygen, because the oxygen is always -2. Everybody else on the periodic table can change, right? You would not have guessed bromine to be +5. Seems very out of character for it. So you always start with the oxygen and figure out whatever's left. Alright, I'm going from +5 to -1. How many electrons do I need to get there? 6, right? I need 5 electrons to get rid of the positive charge, +1 to get to -1. Alright. What do I need to do about these oxygens? Add some water. How many waters should I add as a product? Are the oxygens balanced now? Yes. So how do I fix these H's? Right? This is why I love balancing an acid. Right? You just add water to take care of the oxygens, then you add protons to get rid of the H's, and you're done. Alright. Can I add these two reactions together right now? No. What do I need to do to my tin reaction to be able to balance it out? Multiply by 3. So that these will cancel out. Alright, because I have 6 in but only 2 out, so if I do that, now I have that's not so bad, right? I mean, it's stuff you've been doing, balancing chemical equations, balancing charge, just bigger questions, like bigger molecules. We'll trick through that way. Alright. Officially in your PowerPoint is this one where you balance and base. We'll come back to that. I don't think we're ready for that. We're going to take a little mental break. We'll do that Friday. Let's talk about voltaic cells and how we can get energy out of them. Alright, so let's take my original copper-silver reaction and we're going to build a voltaic cell around it. Remembering the voltaic cells are the ones that make electricity, right? So they're going to push electrons in a way that I can then gather them up and power a light bulb or whatever. Alright, so Hopefully everyone's amazing at drawing, because we're going to draw a picture best you can. Alright, so you're going to draw 2 beakers. Alright, so far so good. Alright, what should be the liquid that's in both of my beakers if I have aqueous solution? Water, right? That's the universal symbol for water. I think everybody knows if you have that, it means you have a beaker with water. Hopefully, I mean, this would be an earthquake, right? If you actually put a beaker on the table and had ripples in it, you're probably having an earthquake, because it normally doesn't make a wave anyway. But everybody knows that's water. Alright, I am going to put my copper 2+ over here and my silver +1 over here. There's a reason for that. Right, so definitely my ions are floating in water. How is copper, what state of matter is copper in as a reactant? Solid. So I'm going to draw it as a stick of metal. Why not? Big old stick. Something like that. And label it CU. Let's see on that side. It'll make sense here in a second. Alright. So everything that's copper's on one side and everything that's silver's on the other side. It's a half reaction, right? I've just drawn the 2 half reactions. Right, so everything copper's in one beaker, everything silver's in the other beaker. Look at my original equation. The copper solid is becoming copper ion. So I draw a symbol saying going in that direction. Copper metal is leaping into solution to become, I imagine it's like cliff diving off of the copper solid. They just fly off and they land into the water and they become an ion. And the silvers are getting out of the pool. They are climbing out to get back onto the piece of silver metal. I have a very vivid imagination, apparently. No one else has thought about that. I mean, cliff diving terrifies me, but I imagine if I was a piece of copper metal leaving the safety of all my other copper friends to jump into the big pool. It would feel like cliff diving. Alright. I am going to connect these. Use my fancy symbology. That's a voltmeter. You can write voltmeter or just V. Either way. Alright. Looking at my original equation, copper 0 going to copper +2. Is that the oxidation or the reduction half? 0 to +2. The oxidation half, right? The oxidation half. So this beaker represents oxidation. What then does this beaker represent? The reduction half. If copper solid is making copper +2, does it give off electrons or does it take in electrons if it's the oxidation half? Gives them off. And it's going to give them off this way. It's going to kick out the electrons and send them over to the reduction half where they need them. And by doing that, I have made electricity that I can power something here in the middle if I want to, like a light bulb or whatnot. Alright. If I was looking at this beaker, what is happening to the overall charge of things in the beaker? If this keeps going further and further and further, what's happening to my plus charges? It's gotten lots and lots and lots of plus charges, right? What's happening to this beaker in terms of charge? It's getting less and less and less. They can't actually happen, right? You can't actually get a beaker that's all positively charged. It's weird. So in order to balance it out, we have this thing. It's called a salt bridge. If it's called a salt bridge, what does it most likely contain? Salt. What's our favorite salt that we use all the time? Table salt. That sounds like an excellent example. If I have a salt bridge full of NaCl, which half of the salt should get into this beaker so that charge equals 0? The Cl minuses. Right? So now that's going to start balancing things out. If I put more Cl minuses in, it takes care of the pluses. So then this side has to have the Na pluses to balance out the fact that the silver pluses are getting sucked out. Alright? Last thing is, while I can call it the oxidation half beaker, that's kind of clunky. So we usually call this the anode. So the anode is where oxidation half reaction takes place, right? If you're thinking about your little battery, there's definitely an anode and a cathode, either top and bottom or side by side. Right, so this one's the anode, this one's the cathode. So here's my little helpful hint, right? Looking at the vowels, the anode is always the oxidation. Those two are always vowels together. The cathode is always the reduction. Those are always consonants. Those always go together. The vowels go together, consonants go together. If you were going to draw this from scratch or look at a thing, we always draw it A, B, C. It's always anode, bridge, cathode. So every voltaic cell always goes A, B, C. Anode gives electrons to the bridge, to the cathode. What do you think about that? Yes. Yep. So if you're looking at it, there's a little label plus and minus. This one's getting more positive, this one's... Nope, those are backwards. That should be this, because it's sucking electrons. That's why. It's sucking electrons, so it has to be positive. And this one's getting rid of electrons, so it's negative. Because it's making an excess of electrons that's sending over here. We'll pick up there on Friday. Draw some more pictures. Bounce some more reactions. Good times, good times.